This lecture is going to talk about transformations and residual plots. So residual plots are going to help us identify whether our model fits the data right. And if it doesn't, then we're going to have to take a transformation of some sort. So let's go back to a the very simple model. So let's say that the true model is 1 plus 2x, and then there's some errors. So this is the ideal situation for linear regression. So if we generated some data points from this, we'd get raw data looking like this. And what we observe is that the line passes right through the scatter as it should. So this is the perfect situation. To the right, we see the residuals. So what we're going to do is plot the residuals. Remember, the residuals are these errors. So how far is each point from the regression line? So we'll plot the residuals against the y hat values. So this is the mean of y, in essence, the estimated mean of y. Now, what you'll see is that there is no pattern. It kind of looks like a snowstorm. So a snowstorm is a good residual plot. If you ever see any sort of pattern, that indicates lack of fit. If we were to go back to R for a second, you can get residuals by saying plot fit. So I have just estimated the new food problem, and you'll see that there's a bit of lack of fit on this on the new food data. So there's a bit of a pattern here. You'll see that the residuals are systematically high on that end, systematically high on the other end, and systematically low in the middle. So what that means is that we could probably improve this model further by adding some transformations. You get a couple other plots as well when you do that plot fit. All right, now I'm going to show you two misspecified models. So these two models are going to correspond to two different problems, and each of these problems will have a slightly different solution. So let's start with model misspecification number 1. I'm going to take a nonlinear model. So pretend that the true model is quadratic. So this is one arm of a parabola. So let's just take 1 plus 2x squared, and I've generated some data from this model. I've added some errors, and so you'll notice that the scatter plot basically follows the right arm of a parabola. Now, suppose that we didn't know that this was a parabola, and we just threw a normal simple linear regression at it, and we've estimated a wrong model. Okay, so here's the line is showing the best linear fit of that parabolic shape, and it's not a really good fit. It's not horrible, but it's not very good either. So what you're going to see is that all the points in the left on the left-hand side are above the line, and then as we move over, the points are systematically below the line, so negative residuals. Then off to the right, we have systematically positive residuals again. So that pattern shows up in the residual plot, and this is not a snowstorm. So we're seeing a definite pattern indicating that we have lack of fit. Now, another type of misspecification involves the residuals being constant. So let's take a true model as being this. We're going to exponentiate 1 plus 2x plus the errors. So what you're going to see is that the residuals are no longer constant. Okay, so that when we exponentiate this line, as the mean of y gets bigger, well, the exponent of that's also going to get bigger. And so the variance is going to get bigger out here. And that's what we see. So we see increasing variance of the errors, and that shows up in the scatter plot. Now, notice that if we were to log both sides, if I took the log of y and if I take the log of the right-hand side, I end up with a simple linear regression. And this hints at the solution for this problem of having the variances of the errors increase with their means. And that is, well, just take the log of y, and that will address the problem. Okay, so in summary, we like our residual plots to look like snowstorms. If they don't, there's usually at least one of two things that are wrong. Okay, so problem number one is that you've got an underlying nonlinear model and you've estimated a linear model. Okay, so here, notice the errors still have constant variance, but there's a pattern that we're not capturing. And so the other problem is when the errors have an non-constant variance, and the remedy is going to be to transform the dependent variable. Okay, so what are transformations? So transformations are going to change the relationship between the causal variable or variables and the dependent variable. Now, when it comes to transformations, there are two reasons why we use them, and those two reasons correspond to the plots I just showed you. Either you have heteroscedasticity, and perhaps you also have an underlying nonlinear relationship. This is really important. So when you've got heteroscedasticity, you transform the dependent variable. When you've got a nonlinear relationship, you translate the independent variable. So sometimes you'll have to do both, but the reason you transform the dependent variables to address heteroscedasticity, the reason you transform independent variables is to address nonlinear relationships. So let's talk about the heteroscedasticity problem first. So I'm not going to say a lot on heteroscedasticity. There's sometimes when I teach this, I will prove some of these results, but the math gets fairly complicated, and I don't plan to do it in this video at least. So all I plan to say in this video is that when you have residuals whose variance increases as the mean of those residuals gets larger, so that's exactly what happened back in model misspecification 2. As the mean of y increased, the variance of the residuals increased. So when you're in that situation, you will take the log of the dependent variable. Occasionally you'll use the square root instead of the log, but one of those two transformations usually works to fix that problem. Now there are some other solutions to this that we'll be discussing later on in the course. So another approach is to use a generalized linear model like logistic regression or Poisson regression, but we'll get to that in a couple weeks. Let's move over to the other situation. So the other situation is where you've got a fundamentally nonlinear relationship. Nonlinear relationships can come in a lot of different forms. However, I'm going to say that most of the time in the data sets, at least that I've worked with, the nonlinear relationships come in one of three forms. So the three forms are either increasing returns to scale, decreasing returns to scale, or if we look 2 pages away, inverted U-shaped. So let's start with increasing returns to scale. So increasing returns to scale, I don't find to be that common, but they do come up from time to time. So I'll give you a quick example of one of these. Let's say that X was the number of jobs that I have running on my computer, and Y is the response time. So if I issue a command, how long does it take my computer to run that program? Okay. What you'll often find is that the response time increases quadratically. So with the number of jobs that you have running. And there are reasons for this. As the processor gets more and more used, and memory gets more used, we have to start swapping out to disk, and things become more complicated, and the response time's slow. So the key point here is that as we go out on the x-axis, the change in y becomes greater. So if we look at a change in x from 0 to 1, that's the run. The rise is pretty small. However, if you go from 3 to 4, well, the change in the curve is much greater. So those, the change in y increases as x becomes larger. That's increasing returns to scale. Decreasing returns to scale, I think, are very common. And so notice that a change from, say, 0 to 1 gives you a very large change, and as you go to the right, the change in y begins to decrease. Whenever you have one of these situations, we're going to use a model of this form. So we're going to transform our x variable by taking the kth power of it. So let's have a couple concrete examples of this. If we put k equal to 2, we get a quadratic model. So any value greater than 1, any value of k greater than 1 is going to give us increasing returns, and the larger the value, the steeper those returns. So k equal to 3, notice that the slope of the curve becomes even greater. Okay, so if we're in a situation where we expect increasing returns to scale, we'll use a quadratic term or perhaps a cubic term, maybe even a quartic term. I've never gone beyond a quartic though. If you expect decreasing returns to scale, you're going to stick a value of k in less than 1. So one of the most important transformations is the square root. So if we set k equal to 1/2, we get a curve like this. We're going to stick the value, for k equal to 0, we're going to put in a logarithm. So logs, one of the other two most important transformations. Square roots and logs, I think, are two of the most important transformations. We could take it further. If you went to the -1 power, you get the inverse function. The inverse root function would be to the -1/2 power. So that's what you do if you have increasing or decreasing returns to scale. There's a very famous quote from John Tukey, and he gives a little bit of advice. You can read this yourself. These are called his first aid transformations. This is, I think, very, very good advice. Whenever you have a log or a count, log it. Sorry, when you have an amount or a count, log it. And so that works 95% of the time. Occasionally there are amounts or counts where you don't want to log them, but usually you do. What do you do if you have a quadratic, well, if you have an inverted U-shaped relationship? So one very famous example of an inverted U-shaped relationship is going to be price and profit. Okay, so if X is price, if I charge very little, I sell a lot of product, my margins are very thin, and I don't make a lot of profit. As I increase my price, my sales are going to go down usually. However, the margins become healthier, and at some point I'm going to reach an optimal profit point. And then beyond that point, well, if I charge way out at this level, my margins are great, but I don't sell very much, therefore my profits are not so good. So that's one example of an inverted U-shaped relationship. So whenever you have an inverted U-shaped relationship, the way to address it is to add a quadratic term. And so a parabola will give us a general all-purpose inverted U-shaped function. A few properties to note. The min or max value, you can differentiate this. If this is equal to y, find the derivative with respect to x, set it equal to 0, and the maximum is going to occur at minus the linear coefficient all over 2 times the quadratic coefficient. This is going to be U-shaped whenever the quadratic coefficient is positive, inverted U-shaped whenever that quadratic coefficient is negative. Sometimes we'll use higher order polynomials, so we can stick a cubic in, but they can become problematic because of multicollinearity, and there's a lot of other issues. I usually don't go beyond a second order. Curvature can change several times. It's hard to think up situations where that happens, at least in the social sciences and business. Perhaps in the physical sciences, the story is different on that, but not in the social sciences. All right, that's it for the basic lecture on transformations.